Great. So good afternoon, everyone. My name is Samir, and I'm a software engineer at Databricks. And today I'm going to talk about BlinkDB. BlinkDB is an interactive query processing framework that supports approximate queries on very large data. So before I start this talk, let me get a quick show of hands of how many amongst you have ever tried to run your queries on small samples of data or small subsets of data to get some quick insight from this instead of executing the whole query that takes a long time. So great. Perfect. So you all are in the right room, right? So with cluster computing frameworks such as Spark, Shark, Impala, Presto, SAP HANA, really trying to push the limits for in-memory computation, one of the natural questions that come to mind is, can we actually do better than main memory? And being better than main memory can actually mean one of these two things. First, can we actually get more with less? Can we actually get the same quality of answers that we get now when we execute our queries over our data sets by using a fraction of resources? If we get some answer right now by using 100 machines, can we get the same answer using 10 machines or maybe a single machine? Second, can fast even get more faster? Can we get the same answer that we are getting now, probably in orders of minutes or tens of minutes, in just a few seconds or even a fraction of seconds? So just to give a kind of brief intuition of the kind of timescales that I'm talking about, let's take a back-of-the-envelope calculation for computing some kind of aggregate on 10 terabytes of data that's spread across 100 machines. For simplicity, let's just assume that we have 100 disks, one attached to each machine. So if we use cluster computing frameworks that are designed to essentially operate on disks, think of Hive, think of Hadoop, the cost of executing a query primarily depends on I/O. It's the bottleneck. You have disk bandwidths which are of the order of 100 to 200 Mbps. So if you're reading around 10 terabytes of data on 100 machines, you pretty much end up spending like tens of minutes in actually reading this data. Then you have computation cost, you have communication costs. So all in all, the query completes between 30 minutes to 1 hour. Now, if we cache this entire data in memory, so now we are talking about cluster computing frameworks that take advantage of this caching. So think of Spark or things like that. The cost of reading this data goes down by probably 2 orders of magnitude. Memory bandwidths are anywhere between 10 to 20 Gbps. So now suddenly, basically loading up this data takes of the order of tens of seconds or probably a minute. And you still have communication cost, you still have computation cost. All in all, it takes around 1 to 5 minutes to process this amount of data. And in this design space, what we really wanted to achieve was essentially sub-second latency. Can you actually get this answer within a fraction of a second, or maybe a couple of seconds? And this is what we wanted to see. So overall, the approach that we take in this project was essentially executing queries on samples of data. What samples of data essentially enable us to do is to not read this entire data at runtime. And not reading this entire data at runtime essentially does not involve this entire overhead of scanning this entire data, which might take like 10 or 20 seconds to just read this data. And all in all, this is what query execution on samples enable us to do. So when we are just, I'll take a simple example just to highlight the basic principle. We have a table that has 3 columns. In this case, we are just reporting certain metric. This is the buffering ratio across all users that are at different locations in the US. So if I ask a simple query, what is the average buffering ratio in this table? A standard database essentially scans this entire 3rd column, tries to compute some average, and return an exact answer, which in this case might be 0.2325. What sampling enables us to essentially create a particular sample. So in this case, you can take a uniform sample from this table in which each tuple is in the final sample with a finite probability. Let's say in this case, it's 1 by 4. Now, what we can do is we can actually execute our query on this sample and get an approximate answer, 0.19 in this case, which can be a good approximation of the original answer. However, this answer itself does not tell anything about how close or how far is this answer from the exact answer. So for this answer to be useful, we essentially would like to associate some kind of error bound to this query. Now, in the presence of error bounds, we exactly know how far or how accurate this particular answer is. And depending on the use case, a lot of these things can actually work even with approximate answers. And just another point is that we can always have bigger and bigger samples from our original data set, in which case the accuracy of the answer increases, and the error that is incurred within those answers goes down by a certain function. Okay? So all in all, what sampling gives us is the smooth trade-off between response time and error, or accuracy. As we operate on bigger and bigger samples, it takes a long time to execute the query, and the error goes down by some function. So all our traditional databases are essentially designed to work at the far end of the spectrum. They always operate on the full data set, try to execute the query with so-called zero error, or 100% accurate answer, and return the result to the user. BlinkDB, on the other hand, is designed to operate in the left-hand side of the spectrum, which is to say that we operate on samples of appropriate size, such that the query execution is interactive. You take 1, 2, 3 seconds to execute the query, and you return an answer, an approximate answer, with some error bar. So if there is one thing that I can just show you to convince you of the power of sampling, it would be this. So this is a simple random example. In this case, we have like a session table in which we are trying to calculate the 95th percentile on 10 terabytes of data that's spread across 100 Amazon EC2 instances. The x-axis here is the fraction of data I operate my query on. So 1 means that I'm looking at the full data set. 10 to the power minus 1 means that I'm looking at a 10% sample, a 1% sample, and so on and so forth. The y-axis here is the query response time, the time it takes to execute the query, the 95th percentile on my data set. Now, the first thing should not come as a surprise. As we are operating on 1/10 the data, we get a 10x fast answer. And the reason is that most of our jobs in these large-scale cluster computing frameworks are actually, the response times are dominated by the I/O. Now, the really cool thing is, if we actually look at the errors that we got when we are operating on these small samples of data, we basically see that if we are operating on a 10% sample, we just get a 0.02% error. Similarly, we can get a 99.93% accurate answer 50 times faster by operating on a 1% sample. And this essentially is the power of sampling. While, of course, the exact error and the magnitude of error and kind of like its distribution depends exactly on the kind of underlying data you have or the exact query that you are trying to compute, the overall thing that I just wanted to convey is this, that sampling as a technique is an extremely powerful technique in which even considerably small data sets can actually give us very, very accurate answers. So overall, I mean, if we look at this error, the error that I just showed, it has an extremely interesting property. This says that typically the error that we get by operating our queries on these samples of data depends on the sample size and not on the original data size. And in general, mathematically, this error is actually proportional to 1 over square root of n. Now, if we just think about it, it is an extremely strong property because it says that irrespective of how my data grows in my warehouse, let's say I have 1 terabyte of data right now. Tomorrow, that data basically blows up to 10 terabytes. In an year, I'm talking about 100 terabytes of data. Irrespective of how large my warehouse grows, a 1 gigabyte sample can give me the exact accuracy on my data set or on my computations, irrespective of how the data is in the warehouse. Now, like all things in statistics, this actually comes with a lot of conditions or implicit assumptions. The assumptions might be what is the kind of sample that you have to create, what is the right size of sample that you have to create, what is the right sample for a particular error distribution, what is the right sample for a particular query, and so on and so forth. And if there is one line that I can actually describe BlinkDB to you, it is essentially aiming towards abstracting all these conditions from the user. So overall, the interface that BlinkDB provides is essentially a SQL. It basically expects a user to enter a SQL query that looks like this, something like select average session time from this table. You might be filtering on a certain attribute, and allows the user to add a time bound to this query. Now, depending on this time bound, we select the right kind of sample, the right size of sample, and return an approximate answer with a particular error that's associated with it. Now, if the user is not satisfied with the particular accuracy, she can always increase the time it takes to execute the query, in which case we would get a more and more accurate answer with a smaller error bound. Okay? As far as the query syntax is concerned, or the parser is concerned, We support all major aggregate functions, all the standard aggregate functions, such as average, count, sum, standard deviation, percentiles, etc. We also have support for filters and the group by clauses in the query phase. We can also do foreign key joins. We can also support nested queries. And last but not the least, one of the most powerful features is actually that we can even support ML primitives or user-defined aggregate functions, like write any aggregate, any mathematical aggregate that you are trying to do in Java or like in any native language, and we can even approximate that to a certain degree. Now, we also support users to add an error bound to this query. Now, depending on this error bound, BlinkDB tries to give you the fastest possible answer that meets those accuracy criterion. So what is BlinkDB? BlinkDB is a data processing framework that's built on Spark that tries to achieve these three things. First, it creates and maintains a variety of uniform and stratified samples from the underlying data. A uniform sample is just a uniform sample in which every tuple or every element that's in the sample has an equal probability of being in that sample. A stratified sample, on the other hand, samples different parts of data with different probabilities. So if there are certain portions of the data that are more important than others, you tend to oversample that part of the data set. We also return fast and approximate answers with error bars by executing queries on these samples. So different queries, different data sets have different approximation techniques. And all in all, BlinkDB tries to execute or calculate these errors under the hood and return approximate answers with these error bars to the user. And one of the key components of the system is that it verifies the correctness of these error bars that it returns at runtime. So as an approximation system, you will never actually get answers or errors that are wrong. If there are certain cases in which the data distribution is so skewed or the error is so contrived or the query is so contrived that we will not be actually able to return the exact error, in which case we can seamlessly fall back to the exact query execution. So you will never get a wrong answer from the system. So let me talk about the sample creation in detail. So as far as the uniform samples are concerned, what BlinkDB allows is to basically add a uniform sampling operator anywhere in the query graph. So let's say I have a simple operator graph, which essentially might comprise of scan, filters, aggregate, and so on and so forth. BlinkDB allows users to add a uniform sampling operator anywhere in the query graph. Now, this uniform sampling operator is very, very simple. All it does is it takes any data sets that coming into this operator, which might, again, be our favorite table, and then it just applies these semantics. These are pretty simple semantics for a uniform sampling operator. It filters with some random probability. It tries to add per row weights. So once you are actually sampling this data, you need some weights to be associated with each tuple so that you can scale back the answers that you execute on that sample data. And you also need these weights to compute the errors accurately. So we seamlessly add these per row weights. And then last, we perform an in-memory shuffle. So we actually shuffle this complete output that we get after the uniform sampling is done. So this shuffle actually enables us to have, so when we actually shuffle this entire sample, any subset of this sample is also a random sample. So this shuffle actually enables us this smooth trade-off between accuracy and response time. So all in all, this is what our final outputs look like. And this, like if you're familiar with the Spark RDD semantics, this essentially conforms perfectly with the Spark RDD semantics. So you can just take this RDD, and you can do any function on top of it. You can use it as a SQL table. You can actually just map it or aggregate it in any way you want. And under the hoods, the weight columns would automatically rescale the answers. They would automatically calculate the error and return the right answer. The stratified sample operator, on the other hand, operates like this. It just can be, just like the uniform sampling operator, it can be inserted anywhere in the query graph. And when it actually gets this table, this corresponding input that you have, it allows the user to stratify across a certain column or even a set of columns. Now, what does this do is that, first of all, it actually splits this corresponding table logically into two input streams. Now, in one of those input streams, the left input stream, it tries to compute some summary of this underlying data that determines what is the sampling probability that we need to sample our data with. So in this case, a simple summary could be just the counts. So in this case, like we had 2 cities in the original table, NYC and Berkeley. We can just compute a simple summary that had 7 NYC tuples and 5 Berkeley tuples. Now, based on these counts, we can actually insert a ratio, a sampling ratio, and this can be essentially determined with whatever stratified sampling logic we want to have in our underlying sampling infrastructure. And with this ratio, it now just joins these 2 tables, the summary table and the original table, on the key that you're trying to stratify on. So in this case, the key is the city table. You just join it with those 2 tables, and then you basically insert a uniform sampling operator that just samples each tuple with the corresponding ratio that we found out here. All in all, what this achieves from a higher level, it samples different portions of the data with different probabilities. And this is useful for a lot of use cases in which you are trying to basically be interested in only a filtered data or only a certain subset of data, as opposed to uniformly thinking about data. So moving on next, it returns fast and approximate answers with error bars by executing these queries on samples of data. Now what this does is, for simple aggregate functions, the one that I showed before, something like average, count, sum, variance, and standard deviation, we can actually leverage central limit theorem. Now, again, like you don't need to actually get into all these details, but I'll just give a very, very brief intuition of what everything is all about. For simple closed-form aggregate functions, we have the standard results from statistics that can be used to approximate the errors that are outputted when we operate on these queries on small samples of data. And all in all, I mean, besides all this math, what this just means is you have these set of plug-and-play formulas. If you want to calculate the count error, you just need the sample size and the sampling probability. If you need to compute the mean error, you just need the sample variance and the sample size. All in all, these are the plug-and-play formulas. You just like execute your queries on these samples, try to put the appropriate values in these formulas, and there you have the error that incurred by operating on these samples. So as far as the query execution graph is concerned, we just like simply modified our aggregate operators that not only returns the corresponding scaled back answer, but it also returns the corresponding error that's incurred by just plugging and playing these formulas. What we have for generalized aggregate function is something which is called statistical bootstrap. And once again, feel free to skip over these details, but in a single slide, or in a single intuitive way, if I want to explain this procedure, it's just trying to figure out what is the distribution of my underlying data when my overlying query, or whenever the query that I'm trying to execute on my underlying data is completely unknown. So let's say I write a user-defined function. In Java, there is no way that I know as to what exactly it's doing. So Bootstrap is this method, a well-known statistical method, that can actually help me approximate the error that's incurred when I operate this unknown query on a sample of data. And this essentially is applicable to any complex and nested queries, UDFs, joins, etc. So all in all, we use Bootstrap for executing all of these queries. So again, like just in an intuitive way, what Bootstrap does is it essentially inserts a resampling operator in your query graph. Now this resampling operator calculates multiple resamples of the same size from the underlying data set and executes a number of these queries, the same queries, in parallel. And you tend to get like a large number of these answers, which are called point estimates. Now, these point estimates are used to essentially evaluate or approximate the error that's incurred when you are operating this query that you know nothing about on these small samples of data. All in all, I mean, as a systems level takeaway, what this just means is you have a small sample of data, you execute these small queries on a multiple number of samples, something like 100 queries or 200 queries, and you can get the error that's incurred by executing these queries on these small samples of data. And last but not the least, we also verify the correctness of these error bars that it returns at runtime. So again, like this procedure essentially tells you whether the error that you have estimated for a particular sample size is correct or not. And in order to do this, again, in an intuitive fashion, what we try to do is we try to achieve, or we try to measure the error that's incurred on very, very, very small samples of data, and then try to extrapolate the upper and the lower bounds of the error that is to be incurred when you are operating on a large sample size. So all in all, without going into the details, if you get more and more data that's actually estimating this error, you tend to achieve a higher estimation accuracy or a verification accuracy. And we see that around 300 data points, like if you just have these 300 small query executions, you tend to get like 97% accuracy. But all in all, the whole systems level takeaway is that the error estimation techniques that we have currently in any statistics literature are pretty rock solid. I mean, they are based on certain assumptions, but they're easy to kind of like make sure and solidify that. The systems level challenge here is that we actually have a lot of small queries if we want to if we want to estimate the error or if you want to verify that the estimated error is correct. So we are talking about 100 queries or 200 queries for Bootstrap, these very, very small queries that estimate the error. We are talking about 300 data points here, and each data point here can, in the worst case, be a Bootstrap queries. So all in all, we are talking about 30,000 really small queries for verifying the error that's there in the system. So just as a takeaway, the systems level question is to actually execute these very, very tiny queries on these small samples of data in order to estimate the error, to verify the error, and so on and so forth, and then leveraging the statistical techniques that are like 30 or 100 years old in our benefit. So what we do is we actually use or heavily rely on this kind of like shared scanning work that has been done in the database community since the last like 10, 20 years. And what we just do is we simply execute the queries, all these like thousands of queries together in the same fashion. What this means is that if you have a query that looks like this, we have a sample and we have like a query graph that returns a particular answer. And this sample might just look like this. It has 4 columns. It has a particular state, age, metric, and just a per row weight that's associated with the query. So one of the first standard database optimization is that if you have this resampling operator that's a primitive of Bootstrap or error estimation, all you can do is you can push it like as far as the up in the query graph. So this is like the standard filter pushdown based techniques you can completely apply to samples as well. So what this does is it actually reduces your data set that you want to approximate the answer on or execute on by like a few orders of magnitude. Now next, what this resampling operator would do, it would basically create these resamples from this original data and then execute your queries on those original data sets. So if you recall, this is how Bootstrap worked. We essentially executed these very, very small queries on these small data sets and then get this range of answers that are then used to approximate the error. What we do instead is just convert to a shared scan thing. So we just scan the data once and then associate these weights from this underlying distribution. And these weights have a very nice statistical property. Again, we don't need to go into these details, but these weights are exactly the distribution that you get when you sample from a Poisson 1 distribution. All in all, I mean, the key thing here is that you can just read the data once and do all the statistical magic behind just in a single scan. So once you do this, you can actually operate on this sample. You can associate a set of 100 weights that compute the Bootstrap. You can associate this set of like 300 data points that compute the diagnostics, all in all in the shared scan in a single query. So this is what essentially the BlinkDB architecture or the BlinkDB execution engine looks like. I mean, there is no magic here. You can pretty much like use any database that you're using now. We just built it on Spark, but you can pretty much use anything, any query processing framework, and just implement shared scanning in that. And once we have shared scanning, you can actually associate these set of weights, these set of statistical weights. These are very, very small bits that you're associating with every tuple to calculate the error and to calculate the set of diagnostics that verifies that error. And each of these weights are just like 4 bits in size. So if you're associating these set of 400 weights, we're talking about a very, very small overhead of 200 bytes per row. This entire thing is embarrassingly parallel. You can pretty much execute this same thing, like depending on the sample size, on 1 machine, on 10 machines, or on 100 machines. Doesn't matter. So all in all, this is what the entire execution engine looks like. So in summary, we have a framework that basically creates and maintains a variety of random sample and stratified samples from this underlying data. We have then techniques for estimating approximate answers and returning error bars and verifying the correctness of these error bars. So as far as the first process is concerned, this is a completely offline process. This happens, the sample creation and all these kind of things does not happen at query runtime because you need like scans over the data in order to create these samples. The second procedure, on the other hand, is an online process. So when a query comes in, you basically look at the query, then you execute your query on those small samples of data, try to estimate the error, try to verify that error, and return an answer to the user. Okay, so overall, this is what the BlinkDB architecture looks like. You have an original table that comes into the system. You have an offline sampling module that creates a bunch of samples from the underlying data set. So you can have uniform samples. You can have a bunch of stratified samples in the system. And these samples are then cached in memory. Whatever samples could be cached in memory. And there are samples which are just like striped across hundreds of disks or thousands of disks that you have in the cluster. Now, when a query comes in, it can just be associated with a time bound or an error bound, depending on which, first of all, the query plan gets created, and then the sample selection module, depending on whatever the time or the error bounds is, tries to select an appropriate sample and an appropriate size of the sample to execute the query on. And finally, a new query plan gets created that kind of like leverages that sample that you have taken. And we essentially execute this on any cluster computing framework. So right now, we support Hive, Shark, and Presto to return a small approximate answer with a particular error bar. So now I'll not like go on harping about like all the performance results we have, but this is what I would just leave you with. BlinkDB is really fast. I mean, this entire shared execution thing gives us immense speed. And what I have done here is I have 3 data sets at my disposal. I have the Conviva data set that is more of it's a Hive data set that's operating on tens of terabytes of data. I have some of the data set from Facebook, and I have some TPCH queries that I can benchmark things on. So what I did, I took the worst performing queries in our analysis. So I mean, you essentially have, you order these queries with like the response time. You take the ones that are completely the worst performers in terms of response time. I took 2 queries from Conviva, 2 from Facebook, and 1 from TPCH, all the worst ones, right? I operated each of these queries on 20 gigabyte samples. And depending on the original size of the data set that each of these companies or the benchmark used, I was basically, these samples were from anywhere between 0.001% to 1% of the original data set. And as a result of these samples, the error, which has nothing to do with the original data, but only on the size of the samples, was anywhere between 1 to 5%. Okay? So here is what we saw. We executed these queries on 5 machines, 20 gigabyte samples. The time it takes to return or to basically execute this query on a whole was anywhere between 1 to 1.5 seconds. The time it takes to estimate the error that's incurred when I'm trying to execute these queries is less than 0.5 seconds. And the time it takes to verify whether this corresponding error was correct or not was of the order of like 1 second. So all in all, we are talking about the worst case results of basically these entirely different data sets. I mean, for those of you who kind of like follow these benchmarks, TPCH is a benchmark that was very popular in the 90s, late 90s. Conviva is a new company. Facebook, has a completely different data set that it tries to operate on. All in all, these pretty diverse data sets, we executed these queries and these widely diverse set of queries, and all of them finished within like 2 to 2.5 seconds. So as far as the BlinkDB architecture is concerned, something that we are doing as part of Databricks is essentially trying to integrate this natively into Spark. And if you are familiar with the Spark architecture stack, we have the Spark core engine at the bottom. And then we have a bunch of these libraries. So we have Shark for SQL, the Spark streaming for streaming computations. We have the MLlib, which is for machine learning. Then we have GraphX. We have SparkR that you'll hear about in the rest of the Hadoop Summit. What BlinkDB does is it tries to add this additional functionality of returning approximate answers on top of SQL. So we leverage all the Spark execution engine. We leverage all the good properties of Shark, the SQL semantics, and everything, and attach this notion of approximate queries on top of Spark. So we also have a BlinkDB prototype that you can play around. And what this prototype does, it provides some additional, some basic set of functionality, and it's available to try it at blinkdb.org. What this does is it allows you to create samples on native tables and materialized views. So you can pretty much use those standard set of sampling operators anywhere in the prototype. It adds approximate aggregate functions with statistical close forms to HiveQL. So it does not support Bootstrap yet. It just talks about average, counts, percentiles, standard deviation, and so on and so forth, and it adds those approximate aggregate functions to this. And finally, it's compatible with Apache Hive, Spark, and Facebook's Presto in terms of storage, SerDes, UDFs, types, metadata. So anything, if you use any of these frameworks for your current cluster computing needs, you can just like patch it up from GitHub and then just try BlinkDB out. Now with this, I actually leave you with an open question that we still haven't figured out the answer for. And the thing is that we don't know what is the right interface for approximate queries. And I would love to hear your opinions on it offline. What we started with, and this kind of like really came out of my PhD research at Berkeley, we just started with time and error bounds. We didn't really take a decision on it, a well-informed decision. We just thought that time and error bounds to queries would be a good interface to provide to users. A lot of people like it. Some people find it useless. A different interface could be essentially continuous error bars. So you are executing your query. You essentially get an approximate answer with error bars that kind of like go smaller over time as you give it more and more time. So this is some work that Joe Hellerstein, who is a professor at Berkeley, pioneered in the late 90s. A third possibility is that we hide the errors altogether. So anything that is like in our car speedometers, our weighing machines, our blood pressure instruments have anywhere between 0.2 to 1% error, but they bound it and not show it to you, which is probably a good interface choice as well. A fourth option is to be more UI UX specific. You have a graph that has a certain pixel density. You don't need precision beyond a certain degree. So you can just like hide it in whatever interface that we are showing to the user. A fifth possibility is being more application specific. So you have machine learning applications, and you can just like approximate parts of it, parts of inputs to it, some primitives, and then you can actually give these answers which approximate things underbill. So with this, I conclude my talk, and I'll be very, very happy to take any questions. We have native Spark integration planned for August release in Spark 1.1, and yeah.
So thank you for the talk. The numbers they have shown for the benchmark is very interesting. So I was wondering, does it include the offline part?
No, it doesn't. It only includes three things, which basically has the query execution part.
So it will be sometimes like, especially like in use cases on Hadoop, sometimes it's not like a lot of query runs on the same data set. So for example, there's a new, so it's important to know, is this more expensive or less expensive than, if I just have a new table and I want to run a query on it?
I see. So that's a great question. So just to repeat the question is that what if, in Hadoop, we sometimes use ad hoc queries. These queries are on tables that I have never seen before and things like that. And how does the response time, in this case, we actually have an offline component that actually takes in those tables, execute some, or create some samples, and then run the query. How does that compare with that? So in case of ad hoc queries, you can pretty much create a sample. Definitely, right? Because all in all, when you are trying to create a sample, you just scan the data once and then create a sample. So the first run, in this case, would be pretty much what you do with using native Hadoop or native any cluster computing framework that you have. Because in both of them, the bottleneck is going to be in scanning this data. However, for subsequent runs, once you have the sample with you, all of these things, all of the subsequent runs on the same data set or on the same sample would be orders of magnitude faster. So for completely ad hoc queries, things that you have never seen before, we do have optimizations that can actually predict what samples do you need. But if we fail, and you, in the worst case, would basically take the same amount of time. And once you have the sample, then you can basically optimize subsequent runs for those queries.
But you can incrementally enhance. For example, if you start, so
Yeah.
you don't need to recompute every time.
Absolutely, absolutely.
You can re-enhance.
Absolutely, absolutely. In fact, for those who are familiar with the HDFS architecture, we actually have these samples on a per block level. So every block in itself can actually have like a set of samples that are associated with it. So if you have like essentially appends to a particular file in HDFS, you can essentially create incremental samples in your system. You don't need to actually recompute the entire warehouse every time you add a new sample. So in TPCH, we actually had like a bunch of line item order tables. I think what we did was TPCH query number 6 that I just showed here. And as far as I remember, there were like around 3 tables, line item and orders were the biggest ones. For Conviva, we had like this one large fact table that had like around 105 columns. So this is what they do. Like, I mean, they flatten their entire warehouse. Facebook, on the other hand, had, I think, 3 or 4 tables that were really big. And I mean, what they did was, so at some point, what they did was they basically like figured out which tables were frequently joined and just flattened it up. Like, so essentially, these were the tables that.
So is there some kind of correlation in error with the number of tables involved in joins?
So just to clarify, what we do in case of joins is we only support foreign key joins. So if I am joining 2 tables that are on a particular column, I make sure that all the unique values of that column are well represented in the corresponding sample that I join. So essentially, when you specify a foreign key, that's when that's when the system knows that this particular table has to be joined with some other table. So if I know that you are always going to join the city column with like some other table, I can beforehand compute a stratified sample on the city column. So the error that's essentially resultant as part of like joining 2 tables is 0, like basically the tuple error. You still have errors that are resultant from the statistical aspect of it, that for each key you can have like certain strata that you can compute error on, and that kind of like is non-correlated. Yeah.
So maybe you explained this and I didn't quite get it. Say we have some time series data, and there's a spike of connections in the middle of the day.
Right.
I can foresee 2 different use cases for sampling. One being we want to sample across like a couple records from each hour, despite the fact that there's a spike, or we want to sample just everything on whole, and if there is a
Right.
spike, then
Perfect.
we'll
Perfect.
end up getting.
Yeah. And
Is there
people
a way
act.
to currently do that, or do you foresee a way to change
So
that
so.
sampling approach?
Right. So as far as the kind of like the standard way of this is concerned, both of these are what people do. The first thing is just like based on uniform and stratified samples. The second aspect of it is like called load shedding. So if you have a sudden spike in data, your current like basically the throughput increases by like 10 orders of magnitude, you can shed the load. We basically support the former in terms of the API, but there is no technical limitation that does not allow us to do this latter. It's just that we, right now, have not integrated BlinkDB with Spark streaming or any streaming-based systems for which you need this use case. But once you do that, there is no way that it is a technical limitation. You can just like specify whatever sampling you need. And in our case, the corresponding sampling ratio was associated with the tuple. You can also have a corresponding sampling ratio associated with the tuple and the throughput of the system at that time. So you can sample saying that, okay, if the throughput exceeds by this, double your sampling ratio and things like that. So you can totally do that.
So then my suggestion would be for like you were asking the question, add that as a SQL function that you can sort of choose.
So definitely, that's a great point. But what I'm just trying to kind of like mention is that you actually need a streaming-based execution engine for that. Yeah, but great point.
So in the example that you picked, you pick one column, and let's say the data has actually more than one column, and you don't know what kind of ad-hoc queries come.
Right.
Actually,
So
suggest that we do offline for every column now.
no. So actually there is like a paper that I published in 2012 that actually solves exactly this problem. So you can actually look at the kind of queries that you have in your data set, and then we can even try to figure out what is the kind of stratified samples that you have to have in the system. You see what I mean? Like essentially, sorry?
Can you do it across all columns?
Theoretically, you can do across all columns, but let's say your table has n columns, right? In the worst case, you need 2 to the power n stratified samples, which basically would be overkill if you have something like 100 columns in your database. So you can theoretically do for all columns, but there is like a lot of research that essentially minimizes the number of columns without actually affecting the error or the accuracy that you get. Yeah.
So when the system is running, if you do a query that's not currently sampled, does it just automatically redo that or do that sample that it needs to do?
So I mean, we basically provide it as a config parameter. You can do that as well, or you can just like, I mean, not worry about it. So I mean, and this is, I think, like a DB administrator choice. I mean, you can choose to essentially create particular samples beforehand and not worry about queries that do not fall into those sample space.
What would happen if a query came in that didn't have those samples? Does it put an error then? Or?
So no. So we just fall back to the original data set.
Okay.
Right? And I mean, the fact that you would want to create a sample or not create a sample is something that we leave the choice to the user.
Sure. Okay.
Great. Thank you so much.